All right, today is section 5, fundamental sets of solutions. So if we let A be an n by n matrix function continuous on an interval I, then the set of all solutions to x prime is equal to A times x is a vector space of dimension n. And the result of this is that to find the general solution to x prime equals A times x, we need to find a basis, remember that word, for the solution space, which consists of n linearly independent solutions, u1, u2, through un. And the general solution is then, this would be the homogeneous solution because there wasn't a plus b or whatever, is a linear combination of these linearly independent solutions. So a basis for the solution space, u1 through un, is called a fundamental set of solutions. The basis is called a fundamental set. That's what we're doing today. And the n by n matrix function u is called the fundamental matrix for x prime equals A times x. We've got another theorem that states that let u be an n by n matrix function defined on an interval I if the column vectors are linearly dependent, then the determinant is equal to 0 for all t in that interval. Notice it does not say if and only if. It just says if they're dependent, then the determinant will equal 0. Which means if we get the determinant equals 0, then it doesn't necessarily mean that they're dependent. Hence, if the determinant is not equal to 0, this is a logic thing, that if this, then that, then the only thing that is also true is that if not this, then not that. So if the determinant is not equal to 0 for just one value in that interval for t, then we say that these guys are independent. All right, so let's do some examples. We're going to just determine whether the following set of vector functions is linearly dependent or independent over the interval of all real numbers. All right, so let's do the first example. You're seeing, are they independent or dependent? So where the first guy is cosine of t and sine of t, and the second one is sine of t and then cosine of t. All right, so my u, capital U, will be the matrix consisting of these two guys, where u1 is my first column and u2 is the second column. Yeah, so let's find the determinant. That'll tell us the quickest. The determinant would be cosine t, sine t, sine t, cosine. It's a 2 by 2, so that means determinant. This was a matrix, so it's got brackets, and then the determinant just has straight lines. All right, so we're going to multiply down the diagonal. This will be cosine squared minus, down the other diagonal will be a sine squared. Now, can we say that this is 0 for every single t value? Well, we got to come up with 1. All you got to do is come up with 1 when it doesn't work. And how about when t equals 0? You would have cosine squared of 0 minus sine squared of 0. Well, cosine of 0 is 1 and sine of 0 is 0. So this is 1, which is not 0. So that means that this guy is not equal to 0 for all t in that interval. And so what that means for us, since we got it was not equal to 0, is that u1 and u2 are linearly independent, since it wasn't equal to 0 for every single t value. All right, let's do another example. If u1 is e to the t 0, 0, u2 is 0 cosine of t and then cosine of t, and then u3 is 0 sine of t and sine of t. All right, so let's find the determinant of this guy. It would be a e to the t 0, 0, 0 cosine of t, and then a 0 sine of t, sine of t. So finding the determinant of this guy, you're going to take e to the t and multiply it times the determinant of this minor little matrix, which would be cosine times sine minus another cosine times sine. And then it would be technically minus 0 times the other matrix, which would be 0, and then plus another 0 times this minor matrix. Well, these two guys are the same, so you end up with 0. But getting the determinant equal to 0 does not ensure dependence. Does not ensure dependence. It's not an if and only if statement. So we got to do it by definition, which means I'm going to do C1 times U1 plus C2 times U2 plus C3 times U3, setting that equal to 0. And what I want to do is solve for C1, C2, and C3. And C is the only way this can happen is if all three of these must be 0. And if that's the case, then they're independent. If I can come up with values that will make this linear combination 0 without them all being 0, then they would be dependent. All right, so what does this mean? This means I've got C1 times U1 was e to the t, 0, 0. And then plus C2 times U2 was 0 cosine of t, cosine of t. And then plus C3 times 0 sine of t, sine of t. And all of that is going to be 0, 0, 0. All right, so adding matrices together, what that gives me now is C1, okay, so all of the whole first row would be C1 times e to the t plus C2 times 0 plus C3 times 0 equals 0. Second row would be 0 times C1 plus C2 times cosine of t plus C3 times sine of t equals 0. And then the third row would be C1 times 0 plus C2 times cosine of t plus C3 times sine of t equals 0. All right, so what do we get from there? From these three, we end up getting that C1 times e to the t is equal to 0. And then these two guys end up being the same thing. So we end up getting that C2 times cosine of t plus C3 times sine of t is equal to 0. Okay, so let's start with this first one. C1 times e to the t equals 0. Well, e to the t can never equal 0, right? So C1 must equal 0. All right. Now, 4. It's more complicated for the C2 cosine of t plus C3 sine of t. But we need to be able to, for all t, come up with values of C2 and C3 that would make it equal to 0. Well, what I notice is that when t equals 0, what I would have is C2 times 1 plus C3 times 0 equals 0. Well, that gives me that C2 must equal 0. All right. When t equals pi over 2, I would get C2 times 0 plus C3 times 1 is equal to 0, which means C3 is equal to 0. There's no values of C2 and C3 that would make, for no matter what value of t you've got, make this equal to 0. There's no, you can't say, remember, it's got to be for every value of t that the C2 and the C3 would work, right? There's no combination of these guys. And so your conclusion is that C1 is equal to 0, C2 is equal to 0, and C3 are all equal to 0. And so here's an example of one where these guys are linearly independent. So here's a perfect example of, you guys asked me before, of, that whole if and then statement. What about how to give an example of one where your determinant is 0, but yet they're independent? There you go. There's one right there. Okay, let's do another example. How about if u1 is e to the t and then 0, u2 is 0 and then e to the t, and u3 is 0, 0. All right, so we got to do this by definition. This is not going to be a square matrix. So C1 times e to the t 0 plus C2 times 0 e to the t plus C3 0, 0 must equal 0, 0. Check to see. All right, so first row gives me that C1 times e to the t plus C2 times 0 plus C3 times 0 is equal to 0. And then row 2 gives me C1 times 0 plus C2 times e to the t plus C3 times 0 is equal to 0. All right, so putting these two guys together gives me that C1 times e to the t is equal to 0. Well, remember, e to the t can't ever equal 0, so C1 must equal 0. And then this one gives me that C2 times e to the t is equal to 0, which means, again, C2 is 0. All right, so we got C1 and C2, but nothing about C3. And so that means that C3 can be any real number. There's no restrictions on that one. So that means that my C1, C2, C3 is going to be of the form 0, 0, A, or you could also factor out the A and make it 0, 0, 1. Any real number for C3. So if I let C1 equal 0, C2 equal 0, and C3 equal 1, then I'm going to get that C1 times U1 plus C2 times U2 plus C3 times U3 is definitely equal to the 0 vector. And so these guys, U1, U2, and U3, are all linearly dependent this time. Yep. All right. Which hopefully when you saw the problem, you saw that, because I don't know, maybe you don't, but we've got 2 here and then an extra third. It just, yeah. Had they not given me that one, right, these two guys would be independent, right? But not that one. That messed it all up. Okay. One last example, different type. Let's go with, it says, given matrix A is 5, and it would help if I was on this page. Sorry about that. 5, negative 3, 2, 0. We're going to verify that U1 equal to e to the 2t, e to the 2t, and U2, which is 3e to the 3t and 2e to the 3t. We're going to verify that these two form a fundamental set of solutions. Of x prime equals a times x, and we're going to also write the general solution. Okay, so let's first show, let's verify that U1 and U2 form, that they actually are solutions first. Yeah. So first we're going to, I want to show that U1 prime is equal to A times U1. And I also want to show that U2 prime is equal to A times U2. So just to show that they're just straight up solutions to this guy. All right, so U1 prime would be taking the derivative of e to the 2t would give me 2 times e to the 2t. And same there. Right, so that's U1 prime. And then I want to see, is it equivalent to A times U1? Well, A was 5, negative 3, 2, 0. U1 is e to the 2t and e to the 2t. And let's multiply these guys. Row times column, right? So it'll be a 2 by 2 times a 2 by 1. So my answer will be a 2 by 1. 5e to the 2t plus negative 3 times e to the 2t. Row 2 times the column would give me 2e to the 2t plus 0 times e to the 2t. Now, well, that ends up giving me 2e to the 2t and a 2e to the 2t, which is equal to U1 prime. Yay! Okay, so U1 is definitely a solution to that equation. Let's check if U2 is. So U2 prime would be taking the derivative of 3 times e to the 3t. That'll be a 9e to the 3t. And derivative of 2e to the 3t would be a 6e to the 3t. Okay, so now let's check, is it equal to A times U2? All right, so A was 5, negative 3, 2, and 0. U2 is 3e to the 3t and a 2e to the 3t. Okay, multiplying row times column, so that's what? 15e to the 3t. You're on 5 times the 3 to the et, and then plus negative 3 times 2 to the et, so minus 6e to the 3t. Row 2 times the column would be 2 times 3, so 6e to the 3t, plus 0 times 2 to the e, 2 times e to the 3t. And when you simplify that, 15 minus 6 will give you 9e to the 3t, 6e to the 3t, and yep, that was equal to U2 prime. Check. Okay, so what does that mean? That means that U1 and U2 are solutions to that equation. Now, in order for them to form a fundamental set of solutions, they also have to be linearly independent. So that's what the next step is going to be. We must now, so this was step one was show that these guys are actually solutions. Step 2 is now going to be show that they're linearly independent. Because to be a fundamental solution, set of solutions, then they are not only solutions, but they're also linearly independent. Okay, so let's just find the determinant. Yeah, let's find the determinant of U1 was e to the 2t, e to the 2t, and U2 was 3e to the 3t and 2e to the 3t. So the determinant would just be multiplied down the bottom here. So that's a 2e to the same base, keep the base, add the exponents, so to the 5t. And then subtract from it, multiplying down this diagonal, which would be a 3 e to the 5t again. All right, so then that simplifies as a negative e to the 5t. And when is that 0? For what values of t is that 0? And it's never 0. So it's not equal to 0 for all t. There's no way negative e to anything. So what that means is, since it wasn't equal to 0, then therefore they are linearly independent. U1 and U2 are linearly independent. All right, so what does that mean? That means that since U1 and U2 are two linearly independent elements in a two-dimensional vector space, they form a basis. And so therefore, they form a fundamental set. All right, so we had to verify that they form a fundamental set. They do. And then the last part is to write the general solution. How you write the general solution is you're just going to write, oh, x is equal to c1 times u1 plus c2 times u2. They're just a linear combination of these two linearly independent solutions. And so your general solution will just be x is equal to c1 times u1, which was e to the 2t and e to the 2t, and then plus c2 times u2, which was 3 times e to the 3t and 2 times e to the 3t. There's your general solution. Not too bad, right? Not fabulous either, but not too shabby. All right, have a fantabulous day. Bye.